Right, so this is Taylor and the Maclaurin series. So in the last section we're talking about is what we're going to do is we're going to find a way to represent any function as a sum of its power series. And so a lot of these is going to be related to a power series and figure out how in the world can we find a sum of it to a certain point, because again all of these are pretty much going to diverge because they just go to infinity. However, at a certain point, what is their sum going to be, or is there any way to represent it according to a certain number of terms using a series representation? Okay, so in order to do this, so forth, is we're going to do a couple things. The first part is, well, is there any way, we can start, like it says, from the beginning. What it means from the beginning is, well, how do we figure out what the coefficients are going to be? So therefore, we could just plug them in, and go forth when it comes to it, because we know a power series is in this format here. So it's a sum of some number x minus a, right, to the certain power. The question is, how do we find that actual coefficient in the front, besides, actually plug it in individually? There's got to be a way, right? Everything in math, there's got to be some quick little arbitrary corporation there. So that's what we're going to talk about first. So to do so, we're going to, we have a series function that, obviously goes to, we have a function that corresponds to a power series. So we're going to start from just f of x. So this f of x is c naught plus c1 times x minus a to the first power plus c2 x minus a to the second power, and so forth down the line. So I'll just go one more. Right? This is a regular old power series portion. And again, the key thing is figuring out what those coefficients are going to be. Okay. So the question is, okay, so remember all these still, this radius converges still between these values, so that doesn't change respectively. Okay. So now if we take the derivative, or in this case, let me quickly do this. If I plug in f of a, meaning if I plug in x equal a, notice everything cancels, we just get c naught. Okay. So therefore, we know our coefficient is just the f of a term. And that's going to be, so if x equals a, the coefficient is just the output when it comes to it, f of a. But if I take the derivative now, because we want to do all the coefficients, not just the first one, so not so bad there. So if I take the derivative of the function, that goes away. This now becomes c, c1, right? Everything else just goes away. This 2 is gone, right? This is just a constant, right? It's a number, so it cancels out. Over here, now we get plus 2c2 x minus a to the first power. This becomes plus 3c3 times x minus a to the second power, and it keeps going in that same process. And again, if I plug in a in the derivative now, well, all this goes away, and we now get exactly that. We get c2. Oh, actually, yeah. So this ends up being c1. Okay, so if we keep this same pattern, take the second derivative. So that goes away. Now this is going to be 2c2. All that goes away. Plus 6c3 x minus a to the second power. And again, we keep going the same process. Again, plug in a in for this value. Now notice, now this changes a little bit. This now just not just become c0, c1. It's actually 2c2 now. And again, if I take the third derivative, we'll just do one more for instance. So here cancels, and this now becomes, oh, this is supposed to be 1. No wonder it's confusing. This now becomes 6c3 plus everything else. So I'll just do one more. It's going to be 24 x minus a to the second power. Oh, actually, first power, sorry, dot plus everything else. So this, if I take the derivative down here, that would have been the fourth term. So again, if you notice, we plug in a into our third derivative. Now this time, it's 6 times c3. So it went from here, here, there, and now there. So what this is saying now, if I want to solve for each individual, right? If I want to solve for this portion, therefore c naught is equal to f of a. C1 is equal to f prime of A, and C2, I just dividing this over, is equal to F double prime of A over 2, and C3 is equal to, well, dividing this over, F triple prime of A divided by 6. So the question is there a pattern, right? So in other words, is there a way I could find like C5, for instance, without, having to do this derivative over and over again, writing this stuff out, and in general, is there a way to find C of n, right? An arbitrary equation to find any constant we actually looking for. And this one can be a little tricky because of that 2 from the 6, right? So why don't we just do 1 here? Okay. And the cool thing is 6, as another way to write it, is 6 is equal to 3 times 2. 2, another way that is 2 times 1. Or more precisely, that's another way to do it. And just a quick little thing. I wasn't expecting you guys to know off the top, but what this hot process is, this is actually the factorial rule. Because 2 factorial is give you 2. 3 factorial gives you 6. Now, what's going on here? Well, we know 1 factorial gives you 1, but there's 1 also 1. 0 factorial also equals 1. That's a tricky one. So this is technically 0 factorial, 1 factorial, 2 factorial, and 3 factorial. So the general term would be f of n, so you're taking the nth derivative, what you're looking for, divided by n factorial. And that's going to give you any coefficient within its power series. So if you flip the page, that's exactly what this ends up being here. So this says, so given any power series representation, so any power series of this format here, therefore its coefficient is given by the formula of C sub n is equal to the nth derivative of A divided by n factorial. And again, this is pretty nice because, again, you could find now any coefficient you actually want within the power series. You don't have to take the derivative over and over and over again and see what in the rule that's going to end up giving to you itself. Okay? But that's the first part. So we did a lot of work for that kind of stuff, but why do we care about that? And that is a precursor of what we really care about is something called the Taylor series of a function centered at a value A. So what this is saying is the Taylor series portion of any function is I can rewrite any series any function I want using a Taylor series polynomial. Okay? Now this Taylor series polynomial has the format looking like this, which means any function we have that can be represented as a power series can be written just like this. Again, this is called the Taylor series centered at A, where now again we just plug in the coefficient we found times its respective power series. Okay? So unlike older cases where we actually had to find the power series itself, here now we actually have the coefficients. It's just instead of finding C0, C1, C2, and all that fun stuff, now we can actually find the actual value in front of it. So the expansion of the Taylor series looks like this, where this is the first term all the way down to the nth term respectively. And again, it's centered at A because it's centered at a certain value we're going to be given, like 5, 4, and then you would plug in that value respectively. Okay. Now, there's this very special case is when A equals 0. So when A equals 0, right, so all that goes away. We just have x here, and x here, right? Therefore, that's called a Maclaurin series. Okay, it's also a very special case of the Taylor series, and that's why it has its own special name. So the Maclaurin series literally is you're plugging in 0 into the derivative divided by n factorial. And it makes it much easier, if you notice, right, finding a Maclaurin series itself. So in most cases, Maclaurin series are much easier to find than Taylor series because, again, it's a special case. When A equals 0, there's not much work to deal with respectively because you're just taking the derivative of however you want terms, plugging in 0, and then just write down the whole list itself using x squared, and so forth. No a x minus a to that power when it comes to it. So it's a little easier to deal with when it comes to that kind of stuff. So let's actually try an example so you can see how all this comes into play and see how in the world are we about to do this using this connected with now it's either Taylor or the Maclaurin series. Okay. So let's do number 1 right here. So it says find the first 4 terms of f of x equals natural log of x centered around 2 using the Taylor series definition. Okay. So when it says centered around 2, what that's saying is we're letting a equaling 2 in this definition. So it's in this case, it's going to be x minus 2, x minus 2, x minus 2. That's what that represents. And in the power series, again, x minus 2. So everywhere you see an a in here, we're going to plug in 2 instead. That's what I use by centered around that portion. Okay. Now, it also says we're going to use this Taylor series definition, meaning we want the first 4 terms of the sequence here. So we want 1, 2, 3, 4. So up to here. So in order to do so, notice we need f of a, f prime of a, f double prime, and f triple prime. So let's do that. So first we'll just put f of a. What that means is all I'm doing to do is plug in 2 in for x. So that's just natural log of 2. So good job. We got our first term. It's that simple. Okay. All right. Next term, or actually next coefficient is going to be f prime. So first thing I do is take the derivative of natural log of x, which is going to be 1 over x, and then plug in 2. Right. So that's f of a. So f prime of a is equal just 1 over 2. Okay. Keep going. Take the second derivative of this is going to be negative 1 over x squared this time. So f double prime of a is now just going to be negative 1/4. Okay. Keep going. And finally, the triple prime, triple derivative, and that's going to be 2 over x to the third. And if you wonder where I'm getting all this stuff, right, this is kind of like what I'm doing. Take the derivative of that. Take the derivative of this is negative 2. There's already a negative here. Makes positive to the negative third power, if you wonder where I'm getting that stuff. Okay. And then plug in 2 into here, you get 2 over 8. I believe you have 2 over 8, which just ends up being 1/4 as well. Okay. So again, the key thing is these are the coefficients, which is the hardest part to get. Right now, we're just going to plug it in respectively where they're supposed to be. Okay. All right. First term, f of a. So it literally is just natural log of 2 plus, okay, the coefficient, which is this, divided by 1 factorial, which is just itself, so 1/2, times x minus 2 to the 1 power. Okay. Next up, plus, but it's going to be minus, so minus 1/4 times, and I'm going to put that 2 factorial on the bottom, so 2 factorial x minus 2 to the second power. Okay, keep going. So again, this is 1, 2, 3. So 1, 2,